Hi, welcome back. This clip we're going to be covering for CS170. It's going to be on Chapter 8, Digitizing Sound. We're going to cover, continuing on from my last clip, which was how do we digitize pictures. We're going to be looking at sound this time. Okay. Um, so just a little bit of reminder or context. We look at sound as something that creates vibrations through air. Okay, so vibrations are pushing the air waves from a particular object, and then those air waves get pushed up and down to our eardrums, and that translates into a sound. Um, so let me go to here. So here you can see a sound wave. And the first concept we're going to talk about for today is basically sampling. Okay, so you can see up here at the top what they call low sampling rate. Sampling is like these vertical lines that you see here. So let's say this is on the order of like a second or something like that. So this is 1, then 2, then 3, then 4, 5, 6, 7, 8, 9. Right? So these are the samples here. So at each sample, you pick up where the spot is on the wave, and you can see because it's what they consider a low sampling rate, the curve is not really that smooth, right? So you go from here to here to here and to here like that. So it's a low sampling rate, so you can imagine that the reproduction of that sound is not going to be that great, right? Even if we do some like curve smoothing and stuff like that, it's not going to be an accurate representation of the original sound. Okay, now you can see medium sampling rate. You can see more of these lines here. That means we're having a higher sampling rate, right? So it's more sampling, and you see the curve starts to smooth out a bit like that. And then down here you see a high sampling rate, so you see a whole bunch of lines here, right? Way more than what you saw at the top here. And you can see the line is getting smoother on this curve, right? So in some ways it's almost like you increase the sampling, you get like a better reproduction of this curve, like so. Okay, so you can keep on doing this to infinity, obviously. So you can have like infinite number of samples to get like a very perfect reproduction of this curve. Okay, obviously you can't really go to infinity. We do have constraints. One of them would be the size of the file to store the sound, let's say. Okay, so there's like this formula here. So you can see here the rate, the resolution, okay, and then the time. Okay, so you're going to have the rate times the resolution over time, and you divide it by 8. Okay, so that's your bits, bytes, and then that translates into your file size. Okay, so we're going to step next into, well, since you can't have infinite number of sampling, what is the right number of samples to come up with a good sound for, or accurate sound for human ears? Okay, and that's where you get into this Nyquist rule for sampling. So Nyquist rule for sampling basically leads to us coming down to a 40,000 hertz sampling rate. Okay, so if the sampling is saying that whatever you need to produce, you want to do twice as fast as that, right? So the highest frequency. So the humans can hear up to about 20,000 hertz, right? Some can go a little bit higher than that. Some people are a little bit less than that. But let's say 20,000 hertz. So if you go by the Nyquist rule, if the high end is 20,000, you multiply it by 2 to get 40,000 hertz for your sampling rate. So back to this picture, all of this sampling rate, we're going to be sampling at 40,000 hertz. Okay, and as it mentions up here, technically it's actually going a little bit faster than that. So you actually end up with 44,000 or so hertz, like so. Okay, so that's all the Nyquist rule means. Generally, we're talking about reproducing sound for human consumption, and that's why this is a very common sampling rate. That's 20,000 top end for human, and 40,000 is what we sample to play, let's say, music or sound back to people. So that's the main thing you want to remember for Nyquist rule. The other thing you want to know about sound is how many bits per sample, right? So that's this, see bit depth right here? This is an important thing to remember here. So similar to here, where the more of these slices or sampling rate that you took, the more accurate the sound. Likewise, you can flip it the other way. So this was going like along the horizontal axis. This is going on the vertical axis. Okay, so how accurate is this? Okay, so again, if you use a very small number, you're gonna reduce your accuracy. Okay, uh, but again, likewise, you can't increase to infinite number of bits just because of size constraints. So the more accurate you want a higher bit depth, but not to the point where it becomes unwieldy to manage from a space perspective. So the bit depth is representing your up and down, your vertical depth. How accurate is that picture? And here we're using basically 16 bits. Okay, so that's the two main concepts here. Right? Let me come back here to reiterate this for you. Sampling goes across this axis here. The more sampling you get, the more accurate you get, and then your bit depth is going along this axis, the vertical, right? And again, the more bits you use, the more accurate you get. On both sides, you're going to be constrained because you want to get the ideal space usage. Now this is the digitizing process. So you can imagine in the real world, normally what you would have is something making a sound here, and then produces waves through the air. It goes to your ear, and then your ear translates that into waves that your brain can understand. Okay, so here with the digitizing process, you're basically picking up these waves as they're coming through, and it pushes into something, let's say a microphone, right? So that picks up, and the computer will translate that into a digital format, okay, based on those samples and bit depth that we talked about earlier in this lecture, okay. And then likewise, when you want to convert it back the other way, you're going to take all of those digital data and play it back into something, basically a speaker, and it will reproduce those sound waves. And if you used a good bit depth and you used a good sampling rate, it will reproduce that sound wave fairly accurately, right? As far as like human consumption, it will be very accurate. Okay, so that's the whole process, right? So you take it from analog, it goes to a conversion process to become digital, right? And then you go to something, let's say a speaker, that will take the digital and convert it back to analog. Similar to what we had with the pictures, the advantages of the digital sound is that you can do manipulation with the computer. So you have too high or too low bits that you want to filter out for whatever reason, maybe to save space. You can remove those, right? So this point here, removing the waves that are too high or too low for humans to hear. You can filter out small errors. You want to change the pitch, right? So you hear this thing with auto tune. So similar to like what we did with the with the bits in the pictures, where you can make them brighter, you can make them darker, you can increase the contrast on them. Same thing for for the sound, right? You want the pitch to be a little bit higher, then you just change the values and shift them up accordingly. And you can base your calculations on how you want to shift those values on any number of criteria, similar to how you took the picture and you took like the high, the mid-range, and the low to shift the colors by different formulas. You can do the same thing on the sound also. So those are pretty analogous. Okay, so I'm going to cut this at this point. The next one we're going to finish up with is digital images and video. So stay tuned for the next lecture. Thank you.